Anyway, talk to me after class if you're interested. Alex, you interested? Yeah. Okay, well, you could probably get out of it because Leela knows about it and she was encouraging her students to go. I mean, you know, I blew off class all the time. It doesn't really necessarily mean you're going to get a bad grade. So we're going to pick up with the op amp. And we talked about these things called amplifiers and how useful they are. I'm actually thinking of, I always want to do a midterm design project, and I may throw something together for next week, but it would involve using op amps. We're going to do a lab on op amps next Tuesday, so you'll get exposure to how to use them. And then I might throw something at you after the lab, which would maybe be something that you'd have to do if you're interested for extra credit over spring break, just as a way to reinforce these things. So it's not just a plug and chug sort of thing. A good design problem would be kind of fun. Op amps open up a lot of possibilities for applications. We talked about these devices which have 3 terminals, and they have well, actually 5, because they have power coming into them. You have to hook up, you know, like plus 12 and minus 12. We're going to need both of our power supplies in our circuit kit to make these work right. And they have a dependent source inside them. And we talked about, you know, how a real op amp has these typical values where the input resistance is very high, which we saw was good because that gives you the most gain. The output resistance is very low. That is good because that also gives you the most gain. And then we talk about the ideal op amp where we just say, what the hell? Let's just make A go to infinity, the input resistance to infinity, and R0 to 0. That will help simplify the analysis. And it doesn't really make that much difference between going from 10 to the 5th or 10 to the 8th to infinity is really, for circuits, it's kind of a small step. Also, you know, these are small steps that are practically infinity anyway. And why not just make this thing go to 0? It makes the algebra a lot easier. And I said the steps are when you have these conditions and you have negative feedback, which is where you have a wire going from the output to the minus terminal of the op amp, you end up with this thing where VP minus VN equals 0, which means VP and VN are the same. And in this case, VN is VO, and that's going to track VP. This is called a voltage follower. And what that means is the output voltage is going to track the input voltage, but it's not going to interfere with it in any way because this is like a really high, this is like an open circuit here where VP is. So it's like you're able to sample this thing with very little current and detect what it is. It's like being able to measure something without interfering with it. Good question about why does VP equals VN. I did some non-convincing hand-waving stuff. And then afterwards, I had this great idea to explain the concept of why VP equals VM. People walked out saying, I'll never figure this out. And I thought, well, this is something we come in contact with all the time, this thing called negative feedback, right? It's been a cold winter. You've used your heat probably quite a bit, and you probably have a thermostat on your heater somehow, unless you just have like a space heater. And the analog with an op amp is that with this kind of voltage follower circuit, what we're trying to do is we're trying to get the real temperature, which is Vn, to match what the temperature we want it to be, right? It's cold outside, so we put the temperature to something, although this says it's actually pretty hot right now. And we have a furnace that's kicked on by the difference between these two values, right? So if Vp and Vn represented temperature, you could imagine how this thing is going to actually work, right? If it's if we want it to be 65 degrees in here, but the actual temperature is really 48 degrees, you're going to take and multiply that difference, which is like 13 degrees or so, by a really big number, right? A, which is infinity. And so what that means is the furnace is going to kick in and it's going to make it really hot. And that air is going to blow all the way right back to where Vn is. So Vn is going to get really hot really fast, right? In fact, it's probably going to get hot so fast, it's going to be like too hot really fast, right? And when that happens, Vp minus Vn is what? Well, it's negative, right? So now it's going to get really cold. The furnace could instantly turn into an ice machine, right? And it's going to drop things down, right? And it's going to do this at the speed of light with a circuit, right? With your heating system, it takes a while for it to settle to close to the right, close to the right value. But eventually, it arrives to the point where it tracks the setting, right? And that's what a voltage follower is doing for us. And the op-amp is doing for us. That's how negative feedback works. It works to nullify the error between what you have on one terminal and what you have on the other terminal. Because you have this giant engine, this giant furnace here, that's going to correct things at the Vn terminal if they're not the same as the Vp. It always wants Vn to be the same as Vp. So that when when things sort of settle down, this is the point where it's just right. The zero here means it doesn't have to change the temperature or anything. It's just going to let things go. That's how you can think about it. And we already saw the inverted pendulum, but for next year we'll have that, right? So that's basically why this works. Does that help? Everybody can kind of see that clearly. And the same thing applies to if you use cruise control on a car. If you have cruise control, it's the same thing. You set the desired speed. It controls the throttle. So if you start going uphill, you start slowing down. It kicks in the throttle, so it boosts your speed. That's negative feedback again. It happens so many places. It happens in your body all the time. If your cells dry out, it makes you drink water so that it keeps everything at equilibrium. So many different ways. And we're just using this now in a simple circuit. What about the proof? Somebody walked out saying, "Can you prove that?" And here we'll go through and just this is in your handout. We're going to go through and just sort of solve this simplified voltage divider circuit. It's simplified. Well, it's not really simplified. We're using real values, except R0. We're sticking a zero. So that makes the analysis a lot easier. So, we have, again, the equivalent of the furnace here is this voltage source, which is A times Vp minus Vn in here. And since Vn and Vo are connected, Vn equals Vo here because of this wire, right? So this is really A times Vp minus Vo. And we can do nodal analysis here. And there's, I think, a problem in the homework where you're going to get to solve with this sort of real op-amp model. And the typical way you do it is with nodal analysis, right? You can do nodal analysis at the Vp node. And at the Vp node, that's this node right here, we have currents going this way and this way have to add up to zero, right? Well, that's going to be V1 minus Vp. These voltages here are node voltages relative to some ground node, right? So V1 minus Vp over, I'm just going to call this R1 so I don't have to write 1,000 over again. This is R1. Plus, and you could say Vn minus Vp here over Ri. That's the drop across that input resistor. And this Vn, again, is Vo. And that has to equal zero. Those two currents have to add up to zero. And at the Vo node, we have simply that with the R equal to zero, there's no voltage drop there. So Vo equals A times Vp minus V0, right? In other words, this voltage here is the same thing that's coming out of this source because there's no, even if there's current flowing, that's a resistance of zero, so there's not going to be any voltage drop there, right? That's like a bare wire. So we're simplifying it a little bit. In reality, it's 50 ohms, but 50 ohms is really small, so it's not going to have much of a difference. It simplifies the algebra a lot. So this is the case if RO equals 0, right? That's the case. We could ignore all these other, we don't have to do any nodal thing. It's just, it's like you've got a voltage source hooked up to a node, so therefore it's defined as that node, as that voltage source. Well, a little bit of algebra will allow you to solve this for VP, so therefore VP is going to equal VO plus AVO over A. I just solved this for VP, right? I subtracted, or I added an AVO to both sides, and then I divided by A. So there you go. And the A that we're using here is 10 to the 4th. So if you actually are, work this out, it's VO times 1 plus A. Well, that's like VO times 10,001 over 10,000, right? And that just equals 1.0001 VO. So again, therefore, VP is essentially equal to VO, which in this case equals VN. So VP equals VN, right? That's sort of the proof here that VP is equal to VN. Now, you can continue this by substituting, this is equation 1, this is equation 2, that's equation 2. And you could substitute 2 into 1. And what you'll have is that V1 minus 1.0001 V0 over R1. I guess I'm not substituting 2 into 1, I'm just substituting, let's just call this, actually let's call this, let's call this equation 2 here. This is what we're substituting. Plus VO minus 1.001 VO over RI equals 0. And this is a very small 0.00, minus 0.001 times VO. And so what we end up is that we get, V0 times, 1.0001 over R1. Anyway, it's kind of tedious, but this equals V1 over R1. V1 is our input voltage there, and therefore our output voltage is just going to be V1 over R1 times the reciprocal of this mess here, which is not that hard once you plug in values to simplify. And this term is just minuscule because Ri is 10 to the 5th, and you got a point, so it really has very little impact. So what this equals is 1.000101 times V1, which is essentially saying that VO is going to equal V1. That's like just saying that, eventually your room temperature meets what your thermostat was set to. And you can now maybe get a sense of why is it helpful to have a really large A in an op-amp? It's like having a really big furnace in your house, right? If you want it to heat up really fast. having a big A could be helpful, and it's it scales the the error by a huge amount, so it's extremely responsive. So the larger the A, the closer those things are going to be to each other. And you can see right now with an A of, because of this thing right here, because with an A of 10,000, right, it really amounted to basically these things are the same. But if A was only like 2, that wouldn't be true anymore. It'd be quite a big error there, right? So it's really helpful to have a really large gain in these things. You're not going to have to work with the real model very often. There's just, I think, one homework problem where you have to kind of solve it this way. So if this seems intimidating, don't worry. There's a real easy way to deal with op amps. They're very simple circuit variations. And basically what we sort of do is we apply the ideal op amp assumptions when you see negative feedback. And again, the ideal op amp assumptions with negative feedback, so ideal, just to kind of remind yourself, these are the ideal op amp. We're going to assume that these are ideal because, even if they're not ideal, they actually come out to be really close to ideal anyway, right? So, and when you work them in the lab, you'll see they're pretty amazing devices. The ideal op amp means that Ri equals infinity, and the consequence of that is that this means that P equals In equals 0, right? And the negative feedback is telling us that because of negative feedback, Vn is going to equal Vp. And in this case, Vn equals Vo. So therefore, and in this case, when Ip equals 0, so this is true because of this negative feedback and this connection of this wire here. And what is Vp? Well, if Ip equals 0, there's no voltage drop across R1, right? So what is Vp? Yeah, Vp is just going to equal V1. So putting those two together, VO is going to equal to V1. And this is the pattern of a voltage follower. This is a very, it's a circuit that you might see occasionally from time to time, and it's just a wire going straight back to the minus terminal. This notion of gain is the ratio of the output to the input, as we talked about earlier. And in this case, the gain of a voltage follower is 1. Sometimes it's referred to as a unity gain buffer, simply because it doesn't put any load on the V1 node because there's no current draw, and it just mirrors what it's doing at the output terminal with a low resistance. So it actually kind of boosts the power at the output. So the ability to drive loads is enhanced at the output as opposed to just the V1. Yeah, Ri equals infinity. And because Ri equals infinity, that's the resistance between here. That's an open circuit. That means there's no current flowing into the op amp at the minus or the plus terminal. That means Ip equals In equals 0. No, R1 is an external resistor we've hooked up to the op amp. So the triangle is what we see, the inside of the triangle is what you see here. That's the non-ideal model. That's a more realistic model of the op amp. You also saw it here and here. So, but normally when we look at op amps, we're going to just look at the triangles, and we're not going to worry about what the input resistance is because it's just going to be assumed to be infinity. And A is going to be infinity. Okay, well, that's not the only pattern for an op amp, and we're going to be looking at a few different examples today. So first is a basic inverting amplifier. This is an amplifier that allows you to control the gain, like whereas the voltage follower is a unity gain buffer. The inverting amplifier allows you to set the gain as the ratio of two resistors. So with the, we have the negative feedback and all that, the assumptions that we make, these are the assumptions. Well, do you see negative feedback on this? Is there a wire going from the output terminal to the minus terminal of the op amp, or some kind of maybe not a bare wire, but a pathway? Is there an electrical connection? You see this connection right here. This is your negative feedback path. If that's not there, you don't have negative feedback, and then the VN the VN and the VP can diverge. They don't have to be the same anymore. But since you have negative feedback, you're going to have IN equals IP equals 0, and VN equals VP equals 0. The assumptions are based on negative feedback with an ideal op amp. Those two sets of constraints kind of fall out, which makes it easier for us to analyze. And we, for all of these op amp circuits, we use nodal analysis to solve. So we do a nodal for, yeah, so, but you want to avoid, in general, you want to avoid applying nodal to VO. Because it's a little bit mysterious, trying to figure out what's the current coming out of the op amp. But sometimes we actually, we need to find that, and in order to find that, then we'll have to, that's an IO, let me erase that. Then you'll have to do nodal at that point. So, so what we do is we can start by doing nodal for the VN node. And what that says is it says here that, let's see, the VN node, and you can see what's happening here. We have a source here, which is going through a resistor connected to the VN node, right? This is our VN node, this is our VP node. Yeah, don't call these 1 and 2, V1 and V2. We should call these VN and VP. It's more descriptive to call them VN and VP here. So nodal says the current I1, right, which is going to be, well, if you have a VI source here, then this node voltage is VI right here, right? So the current I1 is going to be VI minus VN over R1. And then we have to take the current coming through this RF resistor, which is going to be VO, the output voltage, minus VN over RF equals 0. Well, I made a little bit of a mistake here. Up here under the assumptions where I say V0 equals VP equals 0, we don't know that equals 0 just yet. The assumptions with negative feedback is that just VN is going to equal VP, not necessarily that it's going to equal to 0. Did y'all make that correction? Yeah, scratch that out or erase that. But what we do know is that VN equals VP, and we know that VP equals what? In this particular circuit, VP equals what? No, what does VP equal here in this circuit? Yeah, VP is attached to ground. So you can now say, because Vn equals Vp because of negative feedback and Vp is attached to ground, that Vn is going to be anchored to ground there, right? So this implies that Vn is going to equal 0. You're setting your thermostat to 0 degrees, and the output heater is going to adjust everything to make it so that you have 0 degrees at Vn. And so that means you can cancel out the Vn term here, which is nice. You get rid of the number. And that means you can solve this pretty easily. You just have VI over R1 plus VO over RF equals 0. So solving for VO equals plus RF divided by R1 times VI, your input. Wait, what? Sorry, this equals minus. What am I doing? So I saw an F that looked like this. It's minus RF over VI times R1. If you do the algebra, you'll see. And that makes it an inverting amplifier. The inverting is because you have a minus sign in front of there, and the amplifier is the fact that you have RF over RI. The gain is VO over VI, in this case, is going to be minus RF over R1. So if you need your output to be twice as big as the input, you would just make RF equal twice the value of R1. You're going to have an inversion, so when it's big, the other one's going to be, it's going to be flipped negatively. It's going to flip across the, the horizontal axis, across 0 volts. But it will have a magnitude that's twice as big. So if you're hitting it with a sine wave on the input, you're going to get a sine wave on the output, but it's going to be 180 degrees out of phase. And it's going to be twice as big, scaled by RF over RI, RF over R1. So RF is called the feedback resistor. That's the F. And that is the inverting op amp. Now you'll see these in a lot of situations, and you just look for this. The inverting op amp is distinguished by the fact that the input signal is going through a resistor and connecting to the minus side of the op amp. That's different than the follower that we did, where the input signal went to the plus side, right? And because we actually connected to the minus sign, that's why it's inverting. Here's a simple example. Again, you have a 6-volt source, and again, you have negative feedback. You got these 2 resistors here, but now you have a 2-volt source here. Oh, that's interesting. That's a little bit different than what we had before here. If you find a circuit that's just like this, you can use these formulas because these are pretty straightforward. But if there's any variation, you'll have to go back to using KCL to kind of make sure that you derive it properly, right? Here we have a variation where we have a 2-volt source here attached to VP. So what's the effect of that going to be? Well, we're still going to assume that IN equals IP equals 0. So that's these currents here. But in this case, Vn, which is, again, with the minus sign, is going to equal Vp. But what's Vp in this case? It's now equal to 2 volts, right? So it's not always going to be 0. It's whatever Vp is attached to. And we still do nodal for node A, or the Vn node. And what we find is that, well, we've got this current here. This is 6 volts. So 6 minus VA over 20, that's the current going through the 20K, plus VO minus VA over 40 equals 0. And VA is 2. So you have, again, a pretty simple solution, simple formula to solve such that you'll find that VO is going to equal minus 12 volts. Okay, any questions? We're going to do more. So if you're still a little puzzled, you get through repetition, you get that it's actually pretty straightforward. We're going to look at a different pattern. Here you can see a little bit different. What's different about this one compared to this one? Can you notice some similarities? Well, we have some input voltage here, but it's connected, instead of with the basic inverting amplifier where the input was connected to Vn, it's connected here with the non-inverting amplifier, it's connected to Vp, right? You see that? And there is no voltage here at the Vn, it's just going straight from VO to 2 resistors to ground, stopping here at the Vn node. Again, we can make this say Vn, this one say Vp. Again, we have 0 current going into both of these, so that makes nodal analysis pretty easy. In this case, Vn, we still have negative feedback, and Vn is going to equal Vp, which is going to equal Vi. And we do a nodal for Vn, and we find that, well, this voltage here is going to be 0 volts because this is attached to ground. And who wants to try their hand at a term in the nodal equation for Vn? Yep. 0 minus Vn over R1. Another? Everyone knows it's VO minus Vn over Rf. You're just not telling me. Equals 0. But we know that Vn from above, Vn is equal to Vi. So you can do a little bit of manipulation there. VO over Rf minus 1 over R1 plus 1 over Rf times Ri. Sorry, times Vi equals 0. Mason?
Basically, then what makes this a non-inverting amplifier and the other one?
Non-inverting amplifier is where the input voltage connects to Vp. You see that? Yeah, with a non-inverting, Vp is positive, so you're not inverting, right? With the inverting, basic inverting, we have Vi connects to Vm. Yeah, that makes a huge difference. And once you look at a few of these, you'll see there's not too many patterns for them to fall into. So so VO is going to equal RF times 1 over R1 plus 1 over RF times VI. And you can simplify these things a little bit to say that VO is going to equal this term here. You can kind of get common denominators, so it's going to equal, you know, RF times RF plus R1 over R1 RF, which cancels out an RF. So the output voltage VO is going to equal RF plus R1 over R1 times VI. And in this case, the gain is just RF plus R1 over R1. Which is always greater than 0. And in fact, it's always going to be greater than 1, right? Okay, how about an example? Well, here's a circuit that is in the pattern of a non-inverting amplifier, but there's a few more things going on here. So, you know, if it was just like this circuit with where we knew R1 and RF and, you know, we knew what VI was, then we could figure it out without doing nodal analysis over again. We just use this formula. But this is sort of like a non-inverting op amp, but there's some extra resistors and stuff, making it a little more complicated. So we can't just use our formula. We have to rederive the output. But it's the same process. It's just KCL. It's nodal analysis. So we, you know, we realize that this node here is the VP node, right? This accompanies all that. The I going in is 0. I going in here is 0. This is our VN node. And you know, we have to do some additional work here, right? So, well, we know that IP equals IN equals 0. And we know that VP is going to equal to VN, but the question is, what are those? And looking here, since the current here is 0 going into that, what kind of circuit do we have here to look at if we're just trying to find out what VP is? Can you just kind of focus on this part right here? What is that? What kind of circuit is that? Define VP. Well, it's a voltage divider, but if you're not comfortable with that, you can just do a nodal for VP here. And nodal for VP says that you know, 3 minus VP over 4 plus 0 minus VP over 8 equals 0. And that will tell you that VP equals 2 volts, and that's going to also have to equal VN because we have a negative feedback path, right? We do have a negative feedback path in that there's a pathway from the output to the input minus terminal. So we know VN is 2 volts, and now we can do nodal for VN. Nodal for VN says that 0 minus VN over 2, that's this current going up here, plus VO minus VN over 5 equals 0. So then it turns out, of course, that Vn is 2, so we can scratch that unknown out and just put a 2 there. And so then we just have, getting rid of getting common denominators, we have 5 times, or minus 5 times 2, plus 2 times VO equals 0. Oops, but there's a minus 4 in there. So therefore VO equals 7 volts. Because, well, we did common denominators, so we multiplied this times 5 over 5, and we multiplied this guy times 2 over 2. And that 2, which is Vn, got multiplied by 2. I'm going to time for maybe a couple short ones. You'll find current to voltage converters. You've got, what if you have a current source here? Well, current source here, and well, you know, Vn equals Vp. In this case, Vp is tied to ground. And that means you're going to have 0 volts here. And your IS coming here is going to be flowing into this resistor. So you can kind of tell by inspection, right? You're starting at 0 volts and you're pumping IS through R. You're going to have VO is going to equal minus IS times R. Or if you like, you can do nodal for node N. In which case you have IS flowing in plus VO minus 0 over R coming back from the front. And again, that'll tell you that VO equals minus IS times R. So this takes a current source and turns it into a voltage, or any kind of current that you're trying to maybe monitor, and it'll turn it into a voltage that's proportional to that current. There's a sign flip as well, but that can be helpful, and you can always run that into another inverting amplifier to flip the sign back to positive again. You can also have a voltage to current converter. This is actually, so, you know, I told you how you can't really find current sources very well, but this is actually an example of what a current source, you could sort of construct a current source out of an op amp if you configure it properly. If you have an op amp in this configuration with a voltage source here going into the plus side, you've got an RS here, but the current is 0, so there's no voltage drop there. And again, you have negative feedback, right? So you're plugging. What's interesting is you're plugging the load resistor at the output of the op amp, and then feeding that current back to the minus terminal. Again, that's negative feedback. You have an I/O that's kind of flowing back from the front. And this node here is Vn, but Vn, because of negative feedback, is going to be set to Vs, which is the source voltage. So you can do a simple nodal equation for the Vn node. And it'll tell you that 0 minus Vs over R1 plus I0 equals 0. And therefore, I0 is going to equal Vs over R1. So you can kind of have a current that's coming through that load resistor that's independent of the load resistance to a point. I mean, it's only going to work over a certain range of values. But it would be interesting to build one of those and just sort of see how, how constant that current source actually is. Mason? How did I get Vn equal Vs? Well, because with I equal to 0, thank you for asking, with I equal to 0, Vp has to equal Vs here, right? Because there's no current, there's no voltage drop across R. And because of negative feedback, Vn is going to equal Vp. And therefore, yep. And that is, those are like 5 different op-amp patterns. There's also, we're going to look at these tomorrow. We'll look at the summing circuit, how you can add 3 things, 3 voltages together, a difference amplifier, which subtracts one voltage or signal from another, and a cascaded op-amps, op-amp integrators, and op-amp differentiators. And you can kind of cascade a bunch of these together. 70? Yep. That one? Oh, is that the, oh, that one? Okay. You're getting -6. Do I have an error there in the? Did you solve the algebra differently? So 6 minus VA over 20 plus VO minus VA over 40. In this case, VA is 2 because VB is 2. So, well, let's try that out. So you get 3. 4 oh yeah, 4 over 20 plus VO minus 2 over 40 equals 0. So if we multiply everything by 40, we're going to have 8 plus VO minus 2 equals 0. Is that right? So VO looks like -6 instead of -12. Okay, thank you. I'll have to correct that annotated part there. Cool. That's great. People are still finding errors. Okay, see you tomorrow.